In 1969, with the Cold War raging, Soviet designers launch a new threat to NATO forces. Codenamed Flogger, the revolutionary MiG-23 becomes the world's first pure fighter with swing wings. This World War II German prototype fighter, the P-1101, had wings that were straight for low speeds. For higher speeds, they could be adjusted on the ground for two different angles of sweep. Bell, as a company specializing in jet and rocket-driven high-speed aircraft, had for some time been interested in variable geometry. Using the P-1101 as a basis, Bell built the X-5, the world's first flying variable geometry swept-wing aircraft. The X-5 could vary its wing sweep in flight, but it provided more questions than answers to the problem of variable geometry. As the wings swept back, so did the aircraft's center of pressure. Stability was upset and control became difficult, especially at transonic speeds. The Grumman company, with its variable geometry Jaguar prototype, tried to solve the problem by sliding the wing root backward and forward to compensate for changing sweep angles. It was too complex. When the solution came, it was simple. Grumman had hinged the wings of their Jaguar at the roots. Bell had done the same thing with the X-5. But in England, the Vickers-Armstrong company were researching wings hinged outboard of the fuselage sides. In America, NASA picked up the idea and developed it. They found that stubby, fixed wing roots provided enough fixed wing area to virtually eliminate the problem of shift in center of pressure. By 1958, the way was opened for the development of practical variable geometry aircraft. The General Dynamics F-111 was the first variable geometry aircraft to enter service anywhere in the world. In the F-111, the minimum sweep angle was 16 degrees, the maximum was 72, and the full movement from minimum to maximum sweep took 17 seconds. Even though the variable geometry system of the F-111 worked well, the aircraft had a troubled development history. The F-111 project was the answer to a very ambitious defense brief. It was intended to replace all the American Century fighter bombers of the 1950s. It was also charged with achieving what was called maximum commonality, Secretary of Defense McNamara's approach to making major savings in the defense budget. At takeoff, the sweep angle of the wings was 16 degrees, not very far from being straight. The combination of straight wings and full flaps gave takeoff performance similar to a conventional straight-winged aircraft. The action of sweeping a wing back doesn't just change the sweep angle. It also changes the wingspan of the aircraft, and it changes the relative thickness of the wing. Low angles of sweep give high lift and high drag. Also, the greater the wingspan and the thicker the wing, the higher the drag. Higher sweep angles and lower wingspan reduce drag for high-speed performance. As the wing sweeps back, the relative thickness of the wing is reduced, again producing less drag. In the case of the F-111, Once the aircraft had established its climb, the sweep was increased to 26 degrees. This was the standard setting for flying at speeds of up to Mach 0.8, or 8/10ths of the speed of sound. Between Mach 0.8 and Mach 1.1, the angle of sweep was increased to a range between 45 and 72 degrees. Above 20,000 feet, a sweep angle of 45 degrees gave maximum acceleration and all-round performance. At lower altitudes, more sweep was needed to keep the same operational efficiency. The wings could be swept back as far as 72 degrees for high-speed performance up to and beyond Mach 2. But pilots had to be careful not to lose too much speed at this angle, or the aircraft could lose altitude drastically. Changes of sweep could be used to slow the aircraft down quickly. Reducing the angle of sweep to 50 degrees increased drag enough for the wing to act as a kind of air brake. For efficient maneuvering at transonic speeds, the wing sweep was set at 45 degrees. The combination of lift and drag at this sweep angle gave the pilot the best compromise between high speed and low speed performance. In the early 60s, Soviet aviation experts intently studied the F-111's approach to the problems of variable geometry. This is Nikolai Zhukovsky, founder of the Central Aerodynamics and Hydrodynamics Institute, Russia's Center for Pure Aviation Research. It is known as Sagi, and is a close equivalent of NASA in the USA. It's located at Zhukovsky, a city 30 miles east of Moscow. Close by is the Ramenskaya Test Flight Airfield, the Russian equivalent of the Edwards Test Flight Center. Sagi was established in 1918, when the Red Army began to realize that aircraft were important. Very quickly, it grew to become a great center of aviation research. It has a large complex of wind tunnels capable of producing speeds from low subsonic to hypersonic. At Sagi, data from examination of the F-111 project was used to refine variable geometry research that had been going on for some time. As a result, Soviet cynics were convinced that the variable geometry concept had merit. Information on variable geometry was passed out by Sagi to the design bureaus, notably Sukhoi and MiG. Rather than design a new test bed, Sukhoi chose to modify an existing aircraft. The Su-7 was a frontline ground attack fighter with swept wings designed for high-speed flight. Rocket assistance could shorten the long takeoff runs of high-speed swept-wing aircraft, but it couldn't solve the problem of high landing speeds. Sukhoi modified the Su-7 by hinging its wings about halfway along the span. It was a compromise that sacrificed some of the potential benefits of variable geometry, but it meant that a Soviet swing-wing aircraft could be flying fairly soon. When Western observers first saw the Su7 IG at the Domodedovo Air Show in 1967, they didn't take this halfway solution seriously. They thought it was just an experiment, but in fact it became a fully operational aircraft in a family known to the Soviets as the Su-17, 20, and 22. To the West, they were known as the Fitter. About 1,000 were built,